Okay, so we kind of left off kind of understanding how the cochlea works, which is the eardrum is responding to those air pressure waves, which makes the bones move, which pushes the fluid in the cochlea. And remember, it's like a water slide. Fluid goes up, fluid comes back down, goes up and then back down. And as a consequence of that fluid wave, we have things that move. And that's how we hear. That's where we kind of ended up in the last time. So the organ of hearing is called the organ of Corti. Okay? And we're going to look at how that organ works. Okay? Now, I have this picture here to kind of show you where it's located. So here are all the axons of all the hair cells. So let's have a look on this. So here we have, this is the cochlea, and we have all of the channels where the fluid moves, the fluid wave goes up and down. And then here is where the organ of Corti sits. Can you see there? It sits in like the middle kind of chamber. And you know how that we had bony labyrinths and membranous labyrinths. Okay. This is the bony kind of cave, and these are like the membrane caves. So let's have a look and see what sits in there. So you've got these things called hair cells, and they're the cells that are the sensory receptors for hearing. You know how much I love my sensory receptors? Well, these guys are ultra cute. They are absolutely amazing in how they work. There's also some cells there that support the sensory receptors. Okay. So let's have a look and see how that works. I've got a little video here. I'm just going to stop and start it so you understand how it works. Pardon me.
External sound waves are directed by the auricle through the external acoustic meatus to the tympanic membrane. The sound waves cause the tympanic membrane to vibrate.
See?
The tympanic membrane articulates with a chain of 3 bones called the ossicles, which consist of the malleus, the incus, and the stapes.
We saw those 3 bones.
The footplate of the stapes articulates with a membrane covering the oval window, which leads to the cochlea. When the tympanic membrane vibrates, the ossicles transmit these vibrations to the cochlea. From the oval window, the scala vestibuli runs up to the apex of the cochlea, where it is continuous with the scala tympani, which runs down to the round window.
So essentially, this is showing you how the fluid goes up and then the fluid comes down.
Both these corridors are filled with an extracellular fluid called perilymph. Pressure waves travel through the perilymph up the scala vestibuli and down into the scala tympani, arriving at the round window and causing it to bulge out into the middle ear. The cochlear duct lies between the scala vestibuli and scala tympani and is filled with an extracellular fluid called endolymph.
Here we go.
The scala vestibuli and the scala tympani are separated from the cochlear duct by flexible membranes, the vestibular membrane and the basilar membrane. The vestibular membrane vibrates in response to pressure waves traveling up the perilymph of the scala vestibuli.
So if you have a look, this is like up and this is down. This is the up kind of chamber and this is the down chamber.
This vibration is transmitted through the endolymph to the basilar membrane. On the surface of the basilar membrane lies the organ of Corti.
Okay, so this is the business end of the deal. So you've got a chamber going, a fluid going up and coming back down again, and then but the organ of Corti, which is our organ of hearing, sits on this important basilar membrane. Okay.
When the basilar membrane vibrates, the stereocilia on the hair cells of the organ of Corti move against the tectorial membrane.
Okay, so remember how we saw before how the plasma membrane can actually make hairs? So these are called the hairs, the cilia. So it's a cell with hairs on it. So when the basilar membrane moves, the hairs push up against this tectorial membrane, which is stiff. And when they push up, they bend. And when the hair cells bend, that's when they send action potentials.
The movement of the hair cells initiates the conversion of the sound waves into electrical nerve impulses.
So you're going from sound wave, air wave, to fluid wave, and then from fluid wave to action potentials.
A process known as sound transduction. These impulses are later integrated by the brain into our perception of sound.
So there you go. That's how it works. It's pretty amazing, don't you think? And those hair cells, let me just go back a step. So these hair cells, aren't they cute? So those hairs bend, which cause them to fire action to depolarize, which causes them to send action potentials down here. Okay, so they're very, very fit for purpose. And we use these hair cells many times. So we use them for the organ of Corti, but we also use them for our sense of equilibrium. We use the same type of cell. Why fix it if it's not broken? Here we go. So we are now looking at our sense of equilibrium. So our sense of equilibrium is monitored or is kind of related to something called the vestibular apparatus. Okay. All right. So let's have a look at it. And there's two different kinds of equilibrium. And we're going to have a look at that in a minute. So equilibrium, there's two different types, and it's governed by the vestibular apparatus. Here we go. Now, static equilibrium. So this is got to do with you moving with your head with regards to space. So for example, so you're not moving per se. So for example, when you go up a lift, you know you're going up the lift, right? So this static equilibrium is watching what your head is doing in the context of gravity, okay? How is gravity working on your head? So when you go up a lift, you go down a lift, you'll feel it. When you stop in a car, like your body isn't moving, but you're stopping, your car stops suddenly, you feel it, okay? When you're not moving, but your head is kind of tilted, you feel it, okay? So we have, now we're in the vestibule, okay? Remember we had three parts. We had the cochlea, the vestibule, and the semicircular canals. We've seen how the cochlea works. Now we're looking at this bit. What is its job? So in here, the vestibule, we have hair cells again, okay? Look at this, hair cells. Look at them. But these hair cells are actually sitting in some jelly, and on top of the jelly we have crystals. Now we have these things, okay, we have these little kind of contraptions. We have two of them, one sitting in a horizontal direction and one sitting in a vertical direction. Okay, so when we move our head like this, it causes the hair cells to bend, which causes the jelly to pull. Okay, so start again. When we move our head relative to gravity, so when gravity is moving our head, we're not moving, we're under the effect of gravity. The jelly moves. This jelly moves. And so that pulls on our hair cells, which causes them to fire an action potential. Okay? Can you see here? Gravity makes the stones move, which make the jelly move, which causes the hair cells to bend. Okay. And we have two of those. So this, okay, these things, 1 and 2, are called maculae. All right? Maculae. All right? Yeah. Maculae. So this is the bed of receptors. One bed is sitting in the horizontal plane and the other bed is sitting in the vertical plane. All right, so now what we can do is we can look at what happens when our head rotates. So that is called dynamic equilibrium, when your head rotates. So we have one system to detect horizontal movement, one system to detect vertical movement, and another system to detect all the other possible combinations. And these are where the semicircular canals come in. So this looks at rotational movements, whereas these ones, look at straight line, up, down, front, back. Okay? Here we go. So, can you see? So we've had a look at the cochlea. That was part 1. We had a look at the vestibule, which was part 2. Now we're looking at the third part, which is the semicircular canals. In each of the semicircular canals, there's a little swollen bit. That is called the ampulla. We have 3. 1, 2, 3. Okay? And they're at the base of each semicircular canal. Now, this, okay, the swollen bit is called the ampulla, but inside the swollen bit, we actually have this little organ here, okay, and that is going to move in response to your rotational movements. Let's have a look and see how that works. So, if you spin, okay, if you spin, this causes the fluid in here to move. This causes this jelly to move. And then if the jelly moves, the hair cells will bend. And when the hair cells bend, when their cilia bends, it causes them to fire action potentials. Essentially, that's how it works. Right, I think I need to add a little bit here with regards to this picture. Okay, so just adding a little bit more detail. these two things collectively are called maculae. I know there's a lot of terminology, but one of them is called the utricle and the other one is called the saccule. All right, so just make sure you know which one's which. So we have a system for horizontal and vertical movement, and then we have another system where we have fluid in canals, which is rotational movement, and they all work together to tell your brain exactly what your head is doing. Okay, that's essentially what the system is all about. So this one is about the rocks moving, which pulls on the jelly, which pulls on the cilia, which causes action potentials. And then this system here is about the fluid moving, which pulls on this jelly, which bends the cilia and causes action potentials to be fired from those cells. Okay, we use hair cells for hearing, horizontal, vertical movement, and also for rotational movement. Hair cells galore.